So this is the 2014 Junior Cert Higher Level Paper 2, and we're looking at question number 4. Part A says, prove that the angle at the center of a circle standing on a given arc is twice the angle at any point on the circle standing on the same arc. Okay, so this is one of our theorems. For our diagram, we're going to mark a center and draw a circle to begin with. So put the point of the compass there. Stretch the legs out and draw a circle. Okay, now we have to prove the angle at the center of a circle. So let's do that first. Imagine an angle at the center. Like this. So this angle they're talking about here on the given arc, this is the given arc, is twice the angle at any point on the circle standing on the same arc. So standing on the same arc, in other words, starting from here and going up to anywhere else on the circle, back down on the same arc, we're trying to prove that this angle here is twice this angle here. Okay, so I'm going to call the center O. I'm going to call this point A, B, and C. It doesn't matter what you call them. And then I'm going to label this angle here. I'll call that small p. This angle. I'm going to call this angle here small r. So what are we given? We're given a circle . Center O. And we're given the points A, B, and C. On the circle. And we're also given the angles P and R as shown. Okay, so what are we asked to prove? We have to prove that the angle P is equal to twice the angle R. So in order to prove this, what we do is, this is the bit you have to remember. From the point B, you're going to draw a line through the center and extend it out here a little bit. So you don't have to go all the way to the end of the circle, but you're going to draw this line here. Okay, and then you're going to label this point here. At the end, you're going to label this D. Okay, so our construction then was join B to the center O and extend to D. And then what you do is you mark the angles, some more angles here that you've created. So in other words, see this angle here. We're just looking at this left triangle now that we've created. I'm going to mark the angle outside that. We can call that W maybe. I'm going to mark this angle in here. The smaller angle you've created there, we'll call that T. And then this angle down here, we're going to call this angle here S. So we're looking really at the triangle ABO now, the angles there. So that's also part of what we've constructed. We've done the extension and then we mark the angles W, S, and T. Okay, so now we're down to the proof. So for the proof, what we're trying to do, I'm just going to show you this by color. We're trying to show that the angle P is equal to twice the angle R. So we're going to do that first. We're going to, left of this broken line, we're going to try and prove that the angle W is equal to twice the angle T. So the yellow is equal to double the green. That's what we're going to try and do. And once we do that on this side, it will be obviously the same on the other side then, by the same proof. And that will mean that the angle P is twice the angle R. So how do we show that the W angle in yellow is twice the T angle in green? Okay, so our first step is to say, well, in this triangle AOB, we're looking at this triangle on the left now. These two sides, BO and AO, are the same because they're both radii. So that's the first step of the proof. So we can say that OA is equal to OB. And the reason for that is radii. They're both radii of the circle. Okay, so if they're both radii and they're both the same, that means it's an isosceles triangle. And if it's an isosceles triangle, we can say that the angle T will be equal to the angle S, because these are both the base angles of this isosceles triangle. So the angle S will be equal to the angle T. So S is equal to T. And the reason is of the isosceles triangle. Okay, now the W angle is equal to the two green ones together. Now that's an angle fact that the exterior angle on a triangle, in other words, when you extend a side like we've done, the exterior angle created is equal to the two angles inside that are opposite this, okay? The two interior angles. So the angle W is equal to the angle T and the angle S together. So W is equal to T plus S. That's another angle fact, which we can just say it's the exterior angle. In a triangle. Okay, so, but because S is equal to T, or T is equal to S, then if W is equal to T plus S, really we can just say that W is equal to 2T. If we replace that S with T, because they're the same, W is equal to T plus T, and T plus T is 2T. So W is equal to 2T. So we've now proved that the angle W is twice the angle T. So then similarly, we can say for the other side, this angle here, which you would call P, the big angle, minus W, that's that angle, will be equal to twice this angle here, which we would call or minus T. So you don't have to prove this now. You can just say, because you've already proved it, you can just say that similarly the angle P minus W will be equal to twice the angle of or minus T. Okay. So now that we know that, we can say that the angle P, which is this full angle here, is equal to the angle P minus W plus W. So the angle P here is equal to this one and this one together. That's obvious. So P is equal to P minus W plus W. Okay. However, we've just shown that P minus W is this one here, 2 times R minus T. So we can replace this P minus W with this, 2 times R minus T. And we can replace the W with 2T. So P is equal to twice R minus T plus twice T. And if we tidy this up a little bit here, we multiply this out. 2 by R is 2R. 2 by minus T is minus 2T. And we still have our plus 2T over there. So then we end up with 2R minus 2T plus 2T. So the minus 2T and the plus 2T cancel, leaving me with P is equal to 2R, which is what I was asked to prove. If I go back up, to prove P is equal to 2R. So I've done that there. So I can write QED, and the proof is done. Part B. P, Q, R, and S are points on a circle with center O. The angle PRS is equal to 32 degrees as shown. So here we go. Find the angle, the size of the angle SOP. So SOP. So if we're looking for this angle here, well, we know that this will be double the 32 because we've just proved that theorem. So it's going to be 64 degrees. The angle at the center on the same arc is double the angle at any point on the circle. Part 2 says find the angle SQP. So SQP, that's this angle here, SQP. Now SQP, if we can imagine that this centerpiece is gone, the angle S or P and the angle SQP are both on the same arc. So that means they're going to be the same size. That's another theorem. So the angle SQP is actually going to be 32 degrees as well. Finally, part C. A, B, C, and D are points on a circle, as shown below. The line segment AC and the line segment BD are diameters of the circle. So this is a diameter and this is a diameter. Prove that ABCD is a rectangle. Okay, so if we want to prove it's a rectangle, one way you can do that is by proving that the four angles are 90 degrees. So what we can say here is that the angle BAD, that's this angle here, that angle there is equal to 90 degrees because BD is a diameter, and any angle coming off a diameter creates a 90-degree angle. So because BD, as was given in the question, is a diameter. Similarly, we can say that BCD is 90 degrees on the other side for the same reason. BD is a diameter. Then if we look at the diameter CD, or AC, CA or AC, this one here, we can say that this angle here, which is CBA, so the angle CBA is 90 degrees, this time because AC is a diameter. Again, this is given in the question. They tell us there. So this angle here also stands on the circle of the same diameter AC, so that's also 90 degrees. So the angle, this angle here would be CDA. and again for the same reason as there. So we've proved that the four angles are 90 degrees. You can say that therefore A, B, C, D is a rectangle. So that's the end of part C and the end of question 4.